Welcome back to the Deep Dive. Today, we're taking on a pretty critical mission, really. We want to cut through all the jargon, the complexity around digital security, specifically how the internet actually builds trust and keeps communications secure.
No.
So we're diving deep into public key infrastructure, PKI, and also virtual private networks, VPNs. Every time you browse online, maybe shopping or banking, you glance up and see that little lock icon in your browser.
Mm-hmm. That padlock?
That's PKI right there in action. It's like this invisible handshake.
Yeah.
Making sure the site you're giving sensitive info to is, well, actually who it says it is.
Yeah, not some imposter trying to grab your details. And that handshake, it's absolutely foundational. PKI is essentially the framework for secure communication online, especially because the internet itself isn't inherently secure, right?
No, not at all.
So PKI manages the whole life cycle, generating keys, maintaining them, delivering encryption keys, and crucially, these digital certificates. Certificates bind those keys to an actual identity. And the real kicker, it lets two parties trust each other even if they've never met or interacted before online. It builds this hierarchy of trust. It does this by combining different types of crypto, asymmetric and symmetric, and hashing too.
Okay, let's unpack that. The cryptographic part, you mentioned two types of encryption are really central here. First, symmetric cryptography. That's the one with a single key, right? Same key to encrypt and decrypt.
Right. Super fast. But the headache is sharing that secret key securely in the first place.
Exactly. Which leads us to asymmetric cryptography. This seems to be the real cornerstone for PKI. It uses that pair of keys, a public one everyone can see, and a private one only the owner keeps secret.
Precisely.
Why is that pairing such a big deal for security?
Well, it solves that key sharing problem you mentioned. And maybe even more importantly, it establishes identity. Anyone can use your public key to encrypt a message only you can decrypt with your private key.
Oh.
Or they can use your public key to verify a digital signature that only you could have created with your private key.
So no need to secretly pass keys around beforehand.
Exactly. If I can decrypt something with your private key that was encrypted with your public key or verify your signature, I know it came from you. It provides that assurance.
And the sort of tangible output of this binding identity is the digital certificate. We encounter these all the time, probably without thinking. They follow a global standard, right? X.509.
That's the one, X.509. Think of it like a digital passport, really. It's basically an endorsed, verified copy of someone's public key, whether that's a person or a server.
So what are the key bits of information inside that certificate we should know about?
Well, it has the subject's identity details, their public key, obviously, and critically, the digital signature of the authority that issued it. But for practical use, the two really key fields are the validity period, the start and end dates, the expiration.
Can't be valid forever.
Right, and the issuer name. This tells you which certificate authority, or CA, is vouching for this certificate's authenticity, who trusts this. And once you have that verified certificate, it gives you 4 huge security benefits. Identification is one, knowing who you're talking to. Confidentiality, keeping data secret. Also, data integrity, making sure the message wasn't tampered with.
Okay.
And the fourth one, this is a big one, non-repudiation.
Non-repudiation. That sounds important, but maybe a bit abstract. How do we make that concept stick for people?
Think of it as the ultimate digital proof, like a legally binding signature, but digital. Because only you have your private key, only you can create that specific digital signature on a message or document.
Right, only me.
So if your signature is verified using your public key, it's irrefutable proof that you sent it or you authorized it. You simply can't deny it later. Nope, wasn't me, doesn't work.
I see.
That's fundamental for things like online banking, contracts, secure transactions. It's why we can trust them.
Now, managing this massive global system requires specific roles, specific organizations. You mentioned certificate authorities, CAs. They're the ones actually issuing and signing the certificates, the big trust anchors.
They are indeed. They sit at the top or near the top of this trust structure.
But checking everyone's ID must be a huge job. I imagine CAs don't handle all that verification themselves.
Often they don't, especially for large volumes. That's where registration authorities, or RAs, come into play.
RAs.
RAs act as agents for the CA. They handle the often messy work of verifying identity, like checking a person's driver's license or confirming a company's registration documents. They do the legwork.
So they don't issue the certificate itself?
No, they just verify the applicant and then tell the CA, okay, this person checks out, you can issue the certificate. Think of them like a notary public for the digital world.
And all this fits into what you call the hierarchical trust model.
Exactly. Trust isn't just random, it flows downwards. It starts with the most trusted entity, the root CA. Ultra secure, heavily guarded.
The top of the pyramid.
Right. Then trust flows down to subordinate CAs who might issue certificates for specific purposes or regions. And finally, down to the end, entities that's you, me, web servers, devices, anyone needing a certificate.
But wait, if this whole system, this whole digital economy relies on this hierarchy, and, our browsers come preloaded to trust a relatively small number of these root CAs, doesn't that make those root CAs a huge single point of failure, like a massive target?
Oh, absolutely. It's the Achilles heel, if you will. Compromising a root CA is the nightmare scenario for internet security.
Why is it so bad?
Because if an attacker controls a root CA, they could issue valid, trusted certificates for any website, google.com, your bank, anything. They could impersonate anyone perfectly, and all browsers would trust them. It would completely shatter online trust.
Wow, okay.
That's precisely why those root CA private keys are kept offline, in incredibly secure physical facilities under layers and layers of protection.
So certificates don't last forever. They have that validity period, but sometimes they need to be canceled before they expire, right?
Yes, that's revocation. Absolutely necessary sometimes.
What would cause that?
Several reasons. Maybe the associated private key got compromised, stolen, or lost. Or maybe the CA issued it by mistake with wrong information. Or the details of the subject changed, like a company name.
So the certificate needs to be invalidated immediately. How does my browser know if a certificate it just received has been revoked?
Good question. So when your browser checks a certificate, it also needs to check if it's been put on the naughty list. The traditional method was the certificate revocation list, the CRL.
The list, okay.
Yeah, basically a big signed list published by the CA containing the serial numbers of all the certificates they've revoked.
But you said published. How often does my browser download this giant list?
Well, that was the problem. It was published periodically, maybe once a day, maybe every few hours. And yes, clients did have to download it, which could be slow.
But periodically.
Yeah.
That sounds like a gap. If a key gets stolen at 9 a.m. and the CRL only updates at 5 p.m.
You've got it. That's 8 hours where a compromised certificate still looks valid. A huge window of vulnerability.
Yeah, good.
Not good at all. That latency was the major drawback. So to address that, we mostly use something else now. The Online Certificate Status Protocol, OCSP.
Online. So real time.
Pretty much. Instead of downloading a big list, your browser sends a quick query directly to the CA's OCSP server for just the certificate it's looking at. Hey, is serial number 12345 still good? The server gives a quick yes/no/known response.
Much faster, much more current.
Exactly. It eliminates that dangerous time lag you get with CRLs.
Okay, so PKI, with its certificates and CAs and revocation checks, that really handles the who, establishing identity, ensuring integrity, trust.
That's a good way to put it. The who.
But once we're confident about who we're talking to, we still need a secure path for our conversation, especially across the public internet. And that brings us neatly to the second part of our dive, virtual private networks, VPNs.
Right. So organizations need secure connections. Historically, they could lease dedicated private lines like a T1 line. Very expensive, not very flexible.
Old school.
Very. Or they build a VPN, which basically means taking their private network traffic, encrypting it, and then tunneling it securely over the public internet infrastructure.
Using the internet as the highway, but inside an armored car, sort of.
That's a decent analogy, yeah.
Now, before we dig into VPN tech, there's a distinction in terms that seems important. Trusted versus secure. They aren't synonyms here.
Not at all. And it's a critical difference. A network could be considered trusted. Maybe you trust your internet provider not to snoop maliciously. But that doesn't mean it's secure. A trusted network, by itself, doesn't protect your data from eavesdropping or modification by others on that network or further down the line.
So trust is about intent. Secure is about technical protection.
Exactly. A true modern VPN must provide security using both encryption for confidentiality and authentication for integrity. That's what makes it secure over the public wires.
Okay, got it. So what are the main ways people actually use VPNs? What are the applications?
Broadly, you can boil it down to two main applications. First, there's remote control.
Taking over another machine.
Essentially, yes. Think IT support troubleshooting your computer remotely. Your machine basically becomes a keyboard and screen for the remote computer. You're controlling their desktop.
Like a thin client accessing a main server.
Similar concept, yeah. Less common for everyday work, more for admin or support. The second and much more common use case is remote access.
This sounds like what most people think of as a VPN. connecting back to the office network.
Precisely. Remote access allows your computer, sitting at home or in a coffee shop, to securely connect to a distant network, like your company's internal LAN. Your machine acts as if it's locally connected to that network. You can access file shares, internal servers, printers, whatever you'd normally access if you were physically there. It bridges that gap securely.
Sounds fantastic for remote work, almost like a perfect solution. But I suspect there are catches. What are some common limitations or maybe misconceptions about VPNs?
Definitely not a silver bullet. There are limitations. First off, performance. The VPN itself doesn't guarantee quality of service, low latency, no congestion, no dropped packets.
Why not?
Because it's riding over the public internet. The VPN tunnel's speed and reliability totally depend on the quality of your underlying internet connection and all the hops in between. It can be variable. Second limitation, and surprises many people, encrypted VPN traffic cannot be compressed.
Really? Why not? We compress files all the time to make them smaller.
We do, but encryption fundamentally changes the data. Good encryption makes the data look like random noise. It removes patterns and redundancies. Compression algorithms rely on finding those patterns and redundancies to shrink the data.
Ah, so encrypted data looks random, nothing for compression to work with.
Exactly. It's pointless trying to compress already encrypted data. If you want the benefit of compression, you have to compress the data before you encrypt it.
Okay, that makes sense. What else? Any other big caveats?
The classic one,
Yeah.
endpoint security.
The user's computer.
Yeah. The VPN secures the tunnel, the communication path. It does that very well, but it does nothing to protect the computers at either end of the tunnel. So if your remote work laptop gets infected with malware and then you connect to the corporate network via VPN,
You've just given the malware a secure, trusted path right into the company LAN.
bingo. The VPN becomes the delivery mechanism. Endpoint security is still absolutely critical.
So when a company sets up a VPN, they need a device to handle the encryption and manage the connections. Where do they physically put this device? I saw models like edge router, firewall, or a dedicated appliance.
Right. It's about deciding where that VPN processing happens. It's usually a trade-off between cost, performance, and separation of duties.
Yeah.
You can run the VPN software on the existing edge router or the firewall. That's often cheaper, uses existing hardware. But encryption, especially heavy-duty encryption for many users, is very processor-intensive. It takes a lot of CPU cycles. Putting that load on your main firewall could slow down its primary job, which is filtering traffic quickly.
So the third option.
The third option is a dedicated VPN appliance, a separate box whose whole purpose is terminating VPN tunnels and handling the encryption-decryption load. It costs more, another box to manage, but it offloads that heavy processing, letting the router route and the firewall filter without getting bogged down.
Makes sense.
Yeah.
And architecturally, how are these VPNs typically structured? We mentioned remote access.
Remote access is definitely the most common, that host-to-site model for individual users connecting in. But another major one is site-to-site.
Connecting to whole networks.
Exactly. Like connecting the LANs of two different office locations securely over the internet. It essentially creates a private wide area network, a WAN, but using the inexpensive public internet as the transport instead of costly dedicated leased lines. Very popular for multi-office businesses.
Any other architectures worth mentioning?
Briefly, yeah. There's extranet access, which is usually for business partners connecting securely, maybe just to a specific screened part of your network called a DMZ. And even host-to-host for direct secure communication between two specific machines, like a client and a server.
Okay, let's get into the mechanics now. The protocols that actually build these secure tunnels. You mentioned earlier there's a key difference in how they encrypt the traffic, two main modes.
That's right. It dictates what parts of the network communication are actually protected. The two modes are transport mode and tunnel mode. Transport mode is somewhat limited. It encrypts only the original IP packet's payload, the actual data being sent.
Just the data. What about the addressing info?
Exactly. The original IP header with the source and destination IP addresses is left intact, unencrypted. So anyone sniffing the network can still see who is talking to whom, even if they can't read the data.
Okay, so what's the alternative? That must be tunnel mode.
Tunnel mode. This is generally what you want for a true VPN, especially site-to-site. Tunnel mode encrypts the entire original IP packet header, payload, everything.
The whole thing.
The whole thing. Then it wraps that encrypted packet inside a new IP packet with a new header. This new header just has the addresses of the VPN endpoints, like the VPN gateways at each office.
Ah, so the original source and destination IPs are hidden, encrypted inside.
Precisely. It provides much better confidentiality, hiding the identities of the actual communicating devices from the public internet.
Got it. So let's look at the main protocol suites that use these modes. First up, the big one, IPsec, Internet Protocol Security. Been around a while, right?
Decades. It's a comprehensive framework, really a suite of protocols designed to secure IP communications at the network layer. Very robust. It primarily uses two main security protocols. There's the authentication header, or AH.
Authentication header, so no encryption.
Correct. AH provides data integrity proof the data wasn't altered and authentication of the data's origin, but no confidentiality.
Okay, so what provides the encryption?
That would be the encapsulating security payload, or ESP. ESP is the workhorse. It can provide confidentiality through encryption. It also provides integrity and optional authentication. You often see ESP used by itself, or sometimes AH and ESP together.
Now, before IPsec can actually protect data, the two ends need to set up the connection, agree on keys and algorithms. That's the ICA process.
Right. Internet Key Exchange, IKEK. It's the negotiation phase. It actually happens in two phases.
Two phases. Sounds complex.
It can be. Phase 1 establishes a secure channel for the negotiation itself. And there are two main ways to do Phase 1, two modes: aggressive mode and main mode.
Aggressive versus main, what's the trade-off?
Speed versus privacy, essentially. Aggressive mode is faster, only 3 messages exchanged. Quick setup.
The catch.
The catch is that some identifying information about the endpoints is exchanged before the secure channel is fully established, so it's potentially visible to eavesdroppers.
And main mode.
Main mode is slower, uses 6 messages, more back and forth, but it's more secure because it protects the identities of the endpoints throughout the negotiation.
Okay, IPsec sounds powerful, but maybe a bit complex to set up. Let's move to the other major player, TLS, Transport Layer Security. This is the successor to SSL, right? We see it everywhere with HTTPS websites.
Exactly. TLS is ubiquitous on the web, and it's increasingly used for VPNs too, often called SSL VPNs, even though it's really TLS nowadays.
What makes TLS VPNs attractive compared to IPsec, especially maybe for that remote access scenario?
Several key advantages, actually. First, they are often clientless or use very lightweight clients. Why? Because the core TLS functionality is already built into every modern web browser.
No need for users to install clunky, dedicated VPN software, usually.
Right. That also means platform independence. Works on Windows, Mac, Linux, mobile devices, pretty much anything with a browser. Another huge one, TLS VPNs generally don't have the same problems with network address translation that IPsec sometimes struggles with.
Why is that?
Because TLS operates at a higher layer in the network stack, it's less affected by the address translation happening at the network layer. And finally, they're often easier on firewalls. They typically only need a single port open, usually port 443, the standard HTTPS port, which is almost always allowed through firewalls anyway. Fewer firewall headaches.
When we talk about TLS, sometimes we hear connection and sometimes session. Is that just terminology or is there a real difference?
It's a very important performance difference. A TLS connection refers to a single communication link. Establishing it involves the full handshake, negotiating algorithms, exchanging keys, authenticating. It's computationally expensive.
The whole 9 yards every time.
Right. And the connection is typically torn down when the specific communication task is finished. A TLS session, however, represents the security context, the shared keys and parameters established by that initial handshake.
And the benefit.
That session context can be saved and reused for subsequent connections between the same client and server for a period of time.
So you skip the expensive handshake on later connection.
Exactly. Resuming a session is much, much faster than establishing a new one from scratch. It drastically reduces overhead and makes the connection feel much more responsive, especially if you're making many small requests.
Okay, one more protocol to touch on briefly. SSH, Secure Shell. Most people probably know SSH for securely logging into remote servers, replacing insecure protocols like Telnet, right? Or for secure file transfers, SFTP.
That's its primary use, absolutely. Secure remote administration and file transfer. But SSH, particularly the common OpenSSH implementation, server and client, actually has the capability to create a full VPN tunnel as well. It's quite versatile.
How does it structure that secure channel?
SSH itself is layered. It has 3 main components working together. There's the transport layer protocol down at the bottom, handling the initial key exchange, server authentication, and setting up the encryption and integrity protection for the ongoing connection. Then there's the user authentication protocol, which runs over the secure transport layer, and its job is to authenticate the client user to the server. passwords, public keys, etc. And finally, the connection protocol, which takes that single encrypted tunnel and multiplexes it. It allows you to run multiple logical channels over that one secure connection, like a remote shell, file transfers, port forwarding, all simultaneously.
Okay, so pulling this all together, it seems like PKI is the foundation. It establishes who you're talking to, provides that trust and integrity assurance using certificates and CAs. The who,
Mm-hmm. The identity and verification layer.
and then VPN protocols like IPsec, TLS, even SSH, they take that established trust, use the keys managed by PKI, and build a secure communication path. The how, the tunnel itself.
That's a perfect summary. PKI provides the credentials, the trust anchor. VPNs use those credentials to build the secure road. They're really two essential halves of the same coin for secure communication online. And maybe let's circle back to that thought about the root CAs. We talked about the hierarchical model, how everything rests on trusting a small number of these root CAs that come pre-installed in your browser, your operating system.
Yeah, that single point of failure idea.
Exactly. So the provocative thought for you, the listener, is this. Given that our entire global system of digital trust fundamentally relies on placing immense faith to these few centralized organizations, what are the real risks? What does that mean for security, for freedom, when trust is so concentrated? And looking forward, does this inherent centralization push us towards needing, maybe urgently needing, to explore more decentralized models for establishing trust online? What might those look like?
That is definitely something to chew on. What is the true cost, or maybe the true risk, of that secure lock icon we take for granted? Lots to think about there. Thank you for joining us on this deep dive.